Today we're talking about Hardy-Weinberg principle. And Hardy-Weinberg principle is a set of ideas that allows us to predict when populations are not evolving. Now, note that we're not talking about speciation or macroevolution here, the change of populations and more specifically species from one to the next. What we're talking about is microevolution, just the continual changes that happen within populations where the gene frequencies differ. Because evolution just means change, so if the allele frequencies are changing, it actually means that the population is becoming mathematically different or evolving over time. So what Hardy-Weinberg principle does is it predicts something called Hardy-Weinberg Equilibrium, and that just means that it's a state where the allele frequencies within the gene pool do not change. And we do this using a quantitative measure of the allele frequencies, and it's based around two different equations. And if both equations are true at the same time, and the assumptions of Hardy-Weinberg equilibrium are being met, which we'll talk about in a few slides, we know the population is not evolving. So the two formulas look like this. They are p plus q equals 1, and p squared plus 2pq plus q squared equal 1. Now, mathematically, it is actually possible for the first formula to be true and the second formula not to be true. If we go back to the last video, it is not true in this population up here. And the reason that it's not true is not that if you add up the p squared plus the 2pq, which are the homozygous dominant and the heterozygotes, it still will equal 1, but the problem is that p and q cannot be equal for those two equations in this particular population. The second one, though, it is in Hardy-Weinberg equilibrium, and eventually this first population, if the allele frequencies don't change, will turn into the second population. It will come into Hardy-Weinberg equilibrium. So what all of these variables represent is p and q are the allele frequencies. P is of the dominant allele and q is of the recessive allele. Then p squared is the frequency of the homozygous dominant genotype. 2pq is the frequency of the heterozygotes, because remember, you could get the heterozygotes in two different ways. And then q squared is the frequency of the homozygous recessive genotype. So if both p plus q equals 1 and p squared plus 2pq plus q squared equal 1, and p and q are the same numbers for both of them, then you have a population in Hardy-Weinberg equilibrium. Here's an example. We have a bunch of mice. The black allele is dominant to the white allele. The population of mice is 400 mice. There are 207 homozygous dominants, 146 heterozygotes, and 47 homozygous recessives. Well, if we do a bit of math around that, what we'll find is that 207 p squareds gives us 414 dominant alleles. And we get that just by doubling the number of homozygous dominant individuals there are. But what we also have to remember is that each heterozygote also has one dominant allele. So there will be another 146 dominant alleles from the heterozygotes. That gives us a total of 560 dominant alleles in total. Since the population is 400, the gene pool is 800, so if we do 560 divided by 800, that gives us a frequency of 0.7. On the other end of the scale, we can take a look at our white mice. Our white mice are homozygous recessive. There's 47 of them, so there'll be 94 recessive alleles from them, and then another 146 recessive alleles from the heterozygotes. That is then going to give us an allele frequency of 0.30, because we'll have 240 recessive alleles divided by 800 alleles in total. However, this population is not actually in Hardy-Weinberg equilibrium. And I know that just by looking at it, because all of these do add up. Like if you add up the 5200ths, 3600ths, and 1200ths, it does equal to 1. And if you add up 7/10 and 3/10, it does add up to 1 as well. But take a look at this. The 3/10 down here, the Q. Okay, let's square that. What will we get? Well, we would get 900ths, not 1200ths. So I know that this population is not in Hardy-Weinberg equilibrium, because P and Q are not actually the same for these two formulas. Even though we use the same data to calculate them, I can look at this and see that, okay, either this is an evolving population, or there's some assumptions of Hardy-Weinberg equilibrium that are not being met. The white mice are more common than we would expect if this were Hardy-Weinberg equilibrium. So what's going on here? Well, we can't know that for certain, but we can work on finding it out. We do have some core assumptions that we have to talk about for Hardy-Weinberg equilibrium. We assume that there's no mutation in the population, that there's no gene flow in or out of the population. So what that means is no individuals coming or going and taking their alleles with them. We assume the population is very large, because small populations, things can rapidly change. We assume that mating is completely random, and this assumption is practically never met, but Hardy-Weinberg equilibrium still works out pretty well. And we assume no natural selection is taking place. When you are working on a Hardy-Weinberg equilibrium problem, there are a couple things you want to remember. You have to remember that when you look at the dominant phenotype, that is going to be both the number of homozygous dominant individuals and heterozygous individuals. You have no way of telling them apart without doing the core math at P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. You can figure it out that way, but you gotta do the math. You can't just look at it and see which ones are which. The other thing you want to remember is you always want to try to solve for either the recessive allele or the recessive genotype frequency first. If you can figure out one of those two, you can first off solve for the other one because they're directly related to each other, but also you can calculate everything else from that. Because as soon as you have Q, you can calculate what P is. And once you have P, you can figure out, okay, what's the P squared and what's the 2PQ?